Should we start? Are there any questions on whatever we have covered so far? The question is, what are FIR and IR systems? The discussion on this topic was not clear. Let me take this opportunity to clear the doubts in the minds of people. These are the two different classifications of digital systems, digital or discrete time systems. These are types. How these are classified? The classification is done on the basis of the relationship. In general, a discrete time system, a linear time invariant discrete time system is governed by a governing equation k going from 0 to m bk times x of n minus k minus summation k going from 1 to n ak times y of n minus k. This here we have said that the classification is on the basis of this equation. So, if ak are 0 for all k, then what is the governing equation likely to be? It is going to be yn is equal to summation of bk times x of n minus k, k going from 0 to m. And what is its impulse response? What is the impulse response? So, let me take m is equal to say 3. For example, let us take m equal to 3. This equation becomes b0 times xn plus b1 times xn minus 1 plus b2 times x of n minus 2 plus b3 times x of n minus 3. So, this is present output depends on present and past three outputs, sorry, three inputs, all right. Now, let us try to find out its Hn, impulse response. So, Hn, what is Hn? Yn will be equal to Hn if xn is equal to delta n. When we write this, we try to find out what is Hn. So, initially relaxed system, x minus 1, x minus 2, x minus 3 are all 0, and y minus 1 is also 0 if required. So, what is y of 0? From here y of 0 is b0 times x of 0, and when xn is equal to delta n, what is x of 0? It is 1. So, y0 is b0. What is y1? y1 is xn is 0. Now, xn minus 1 becomes 0, n minus 1 becomes 0. So, n equal to 1, this becomes 0, all right. So, this becomes 1. So, y1 becomes b1, y2 becomes b2, y of 3 becomes b3, and y4 becomes 0, all right. These are actually what? These y0, y1, y2 are h0, h1, h2, h3, this is h4 and so on. So, all h4s, I mean hn is equal to 0 for n greater than 4, is equal to 0 for n less than 0. So, what is the length of impulse response? So, h of n will be equal to b0, b1, b2, b3, that is all. So, the length of the impulse response is n is equal to 4. So, is finite length. This impulse response is of finite length. Hence, such a system where AKs are all 0 are called as finite impulse response systems. Otherwise, when any of the AKs, even if one of the AKs is non-zero, then you see the present output depends on present and past inputs and one past output, and that one past output is never going to be 0, because the past values are already present everywhere. So, that is why it becomes infinite impulse response length. Last time we have seen one example which is minus a to the power n u of n. Hn was equal to, for a simple system, when y of n is equal to xn minus a times y of n minus 1. This was the system. When we tried to take xn is equal to delta n, yn becomes hn. Initially relaxed system, that means y of minus 1 is 0. So h0 becomes x0, which is equal to 1. h1 is equal to y1. So it is x of 1, which is 0, minus a times yn minus 1. What is yn minus 1? It is 1. h of 2 is equal to 0 minus a times minus a. h of 3 is equal to 0 times minus a times minus a square, and so on. So like this it becomes, in general, hn is equal to minus a to the power n for n greater than or equal to 0, which means minus a to the power n into u of n. What is the length of impulse response? Length of impulse response is infinity, because u of n is a infinite duration signal, infinite duration sequence. Un is present for even u infinity, which is equal to 1. When n equal to infinity, u of infinity is 1. So this length of the impulse response is infinite, and such a system is called as infinite impulse response, or in short IIR systems. All right, very important things as regards to system classification with reference to discrete time systems. Discrete time systems can be characterized or classified in two different ways. One is finite impulse response, the other one is infinite impulse response. Is it clear? Present output is a function of present and past inputs and past outputs. This is a linear time invariant system characterization. When AKs are 0 for all k, that means this term does not exist. Only this part. That automatically means it's an FIR system. The same systems can be classified in one more way, which is called, so y of n is equal to summation of bk times x of n minus k minus summation of ak times y of n minus k, k going from 1 to n, k going from 0 to m, is a difference equation that governs an LTI system. These systems can be classified as recursive and non-recursive. Recursive and non-recursive. From the words you will come to know that when AKs are all 0, the systems are non-recursive. The current value does not depend on the past value of the output. Current value only depends on present and past inputs. So it is a non-recursive, it does not recurse. It is like, what is the recursion? Examples of recursion that you know are factorial. 5 factorial depends on 4 factorial. N factorial depends on n minus 1 factorial. That is the recursion. So when n factorial depends on n minus 1 factorial, it means it depends on the past output. Or Fibonacci series has the present value of the term in the Fibonacci sequence is going to be sum of the past two values. That's a Fibonacci sequence. It's a recursion. All right. So in such a case, the system could be called as, whenever the system has the present output depends on past output, any of the past outputs, it becomes a recursive system. All right. So recursive, that means what? When ak is 0 for all values of k, the system becomes non-recursive, which means finite impulse response. When it is a function of the past output, recursive means IIR. This recursive and non-recursive is a realization. I can realize a system to be recursive or non-recursive. All right. Recursive systems are IIR systems. Non-recursive systems are FIR. FIR systems could be realized in a non-recursive way. IIR systems are always recursive. But there is one but here, in which it says that FIR, there is a possibility of FIR systems being realized using recursive realization. All right. Let's see what is that. It says it can be, it is not necessary. This is necessary. Non-recursive is FIR, recursive is IIR. But converse is not true all the time. Some systems, some FIR systems can be realized recursively. One such example is, suppose if I write y of n is equal to x of n plus x of n minus 1 plus x of n minus 2 plus x of n minus 3. I have taken all bk in the last system equal to 1. All right. B0 is 1, B1 is 1, B2 is 1, B3 is 1. You write y of n minus 1. What is y of n minus 1? N replaced by n minus 1. So it is x n minus 1 plus x n minus 2 plus x n minus 3 plus x n minus 4. Now subtract the second equation from the first. What you will get? You get yn minus yn minus 1 will be equal to xn minus 1 cancels with xn minus 1, xn minus 2 cancels with xn minus 2, xn minus 3 cancels with this xn minus 3. What remains is only x of n minus 4. So I can write this equation as yn is equal to xn minus xn minus 4 plus yn minus 1. This equation is a non-recursive equation. This is converted into a recursive equation. Same equation doesn't change, right? What is done here is a small algebraic manipulations have resulted into this equation equivalent to this equation, which means here the present output depends on present input and past inputs, so also past output. This equation has got a finite impulse response system. Impulse response of this system is finite impulse response. This system is finite impulse response system started with non-recursive or FIR, where all bk's are 1. So it's a finite impulse response system that can be realized by using a recursive relation. Only some cases it's possible, not all. So it in general means recursive systems are IIR, non-recursive systems are FIR, but the converse is not always true. Converse means IIR systems could be recursive, IIR systems cannot be non-recursive. But FIR systems can be realized as a non-recursive system or a recursive system. The system here taken, which is an FIR system, if you implement this using this equation, it becomes a non-recursive realization. If you implement it by using this equation, it's a recursive realization of the same system. All right. Any questions so far? Any other questions? Assuming no questions, let us proceed further and see what are the basic blocks of discrete time systems, discrete time or digital systems. Look into the equation. A analog counterpart has a governing equation which is linear constant coefficient differential equation. When you are trying to implement this differential equation, what do you get in the form of its realization? How do you realize a differential equation? Say for example, d2y by dt2 plus dy by dt plus yt is equal to some xt. Or some dx by dt. This equation was obtained, as you remember, a simple RLC circuit. If you take a series RLC circuit where this is R, this is L and this is C. So what is the corresponding equation, governing equation of this system? This is R times IT plus L di by dt plus 1 over C integral I dt is equal to what? Vt. When you differentiate it once, what do you get? You get L d2I by dt2 plus R di by dt plus 1 over C it is equal to dv by dt. Put here all RLC equal to 1. What do you get? You get this equation where yt is your it, which is response, vt is your input. So a differential equation can be realized by using this. There could be many ways of realization of a differential equation. A one simplest realization is like this. I would have well taken another realization in the form of a parallel RLC circuit. Write the differential equation corresponding to this. Here I will be the input and V will be the output. Is it right? I1 plus I2 plus I3. I will be equal to I1 plus I2 plus I3. Alright. So this is V by R. This is V by or 1 over L integral V dt. What is this? C dV by dt. So all this summation will be equal to IT. So there V would have been input and I would have been output. Or the other way around, I would have been input and V would have been output. Alright, response. So the same differential equation could be realized in multiple ways. It could be a series, it could be any topology that you add. Any combination of RLC is going to give you a second order differential equation. It could be RL series and this parallel, or this series with this parallel combination, and so on. There could be n such possibilities of circuits which can realize a differential equation. So, any differential equation can be realized by using a combination of RLC. That is why RLC forms the basic elements of an analog system. Now, what are the basic elements of a discrete time system was the question in front of us. Okay? So, what could be they? Now, here remember xn and yn are sequence of numbers. What are the operations that you can perform on sequence of numbers? What are the operations that you perform on sequence of numbers? Xn is the input. I multiply this xn by some a. What is the output? A times xn. So, scalar multiplication that you can perform. Alright. This weighted arrow indicates it is a multiplier. Actually, this block is equivalent to a multiplier block where you are multiplying a by xn. What is the output? Output is yn, which is equal to a times xn. I have declared this to be a multiplier. How would you say it, Summer? Summer, I declare it like this. This is my summer. It's up to me what is the block to be used. All right. So, definition of a block it's a times xn. This same thing could be realized. The same thing could be represented in the form of a signal flow graph like this. This signal flow graph is actually data flow graph, because here xn is a sequence of numbers. I can add the two numbers. So, I have a simple block wherein two arrows meet at one place. So, if this is x1n, this is x2n, y of n output will be equal to x1n plus x2n. This is equivalent to a block that is summer. This is x of n, x1n, this is x2n, this is y of n. This is multiplication, this is adder. This is 1 by 1 point addition. x11 gets added with x21, x12 gets added with x22 and so on. It is point wise addition. Equivalent data flow diagram uses this symbol. Whenever two arrows meet at a place, the node is called as an adder. The node is called as an adder. Whenever two arrows meet at a place, the node is an adder. These are digital circuits. Adder is a digital circuit, 8-bit full adder or 8-bit carry look ahead adder, alright, or any other adder, maybe bit serial adder. Whatever adder it is actually an 8-bit adder. The inside structure of that adder could be a full adder, 8-bit full adder with first the least significant bit using half adder, and all others will be full adders, 1-bit full adders. So, it makes an 8-bit full adder or 16-bit full adder, depends on what is this arrow. If I write here 4, it means it is a bus of 4 bits. If I write it to be n, it is a bus of n bits. So, in that case, if it is an n-bit bus, then this multiplier is an n-bit multiplier. If it is an n-bit bus here, then all the adders are n-bit adders. Remember friends, two n-bit numbers when get multiplied, you get a number which is 2n minus 1 bits. So, you need to curtail, you need to cut into n bits. 2n minus 1 bit number is to be cut into, is to be quantized into n bit number. There is a numerical inaccuracy. We are adding an error here. All right. If I represent this as a number of 2n minus 1 bits, then somewhere else you get a multiplier which is 2n minus 1 and an n, which becomes 3n minus 1 and so on. So it would be infinitely growing. The word length required for consecutive multipliers will grow. In order to avoid that, what we do is we declare the architecture to be an n-bit architecture. N-bit architecture means it will have n-bit multiplier, where two n-bit numbers multiplied will realize or will give you another n-bit number with errors, with permitted errors. Alright, two n-bit numbers when added will result into n plus 1 bit number. There also you need to cut it by 1 bit, so that two numbers input are n bit, the output also is n bit. Alright, that is a realization problem in discrete systems or digital systems. That can be looked after separately. It is not part of this course. This part we will try in details in the course of digital signal processing. And the third and more important block is what is known as Z inverse. This is a delay block. If xn is the input, output y of n is y of n minus 1 or x of n minus 1, represented by, actually this should have been here, and the equivalent data flow graph is an arrow weighted by Z inverse. Arrow weighted by a number is a multiplier. Arrow weighted by a Z inverse is called a delay. So it is xn here, y of n is equal to x of n minus 1 here. What is this? You understand adder. Just now I explained you an adder, full adder, 8-bit full adder, n-bit full adder, 16-bit full adder, 32-bit full adder. It could be adding two floating point numbers, it could be adding two double precision numbers and so on. A multiplier similarly is an n-bit multiplier. These are all combinational logic blocks with reference to digital circuit, whereas the only sequential block that is present in the architecture of discrete time systems is Z inverse, which is delay, and this delay is nothing but any of the flip flops, delay flip flop, JK flip flop, SR flip flop, or any other flip flop. What does flip flop do? Flip flop delays it by 1 clock cycle. Any input that you give to a flip flop is delayed by 1 clock cycle. So if the input number is given at one point of time, say t equal to t, if you want to delay it by 1 second, what do? You design a D flip flop which gives a delay of 1 second, so that after 1 second, whatever is the input at the D flip flop will be on the output. This is a block that is equivalent to D block. Now when number xn is 8-bit number, so I have to connect 8 synchronized flip flops. Synchronized with what? Synchronized with a clock. All the flip flops, when they are synchronized with the same clock, they work in the same fashion. Alright. So if it is 8-bit architecture, this line has to be 8-bit. If it is 32-bit architecture, these lines have to be 32-bit. It means there are 32 D flip flops connected in parallel, connected with by the same clock cycle. Although we'll have different inputs, but are synchronized by the same clock. So these are the 3 basic building blocks of a discrete time system. I will take only one example because detailed examples are going to be covered in the course of digital signal processing. Just to give you an idea how the digital system looks like, or how the discrete time systems look like, what is its realization. When you say a differential equation, we have seen the realization. So a difference equation, what does it realize? What is the system that is realized by this equation? So once again we start with, remember friends, the basic equation is the same. I have to rewrite it so many times. Summation of bk times x of n minus k minus summation of ak times y of n minus k. K going from 0 to m, k going from 1 to n. What is this equation? How do I realize this equation? This equation can be realized by using, number 1, software. So there could be a software realization of this equation. software running on a general purpose processor. Number 2, it could be a dedicated hardware. This could be a dedicated hardware as well. That is why digital systems which are realized in the form of software running on a general purpose processor, we call it as software realization. If you design a system in the form of a hardware, the same also can be done, and which is called as a dedicated hardware or a hardware realization of the system. Now, what is the realization? Realization can be viewed by using what is known as a data flow graph. Okay? So, we use the basic symbols, basic block diagrams, basic blocks of the discrete time system to make a full system realization, data flow graph of a full system realization. Let me take a small example, whichever we started with. Y of n is equal to xn minus a times y of n minus 1. How do we realize this system? A first order system, how do we realize it? So, take y of n, I want the y of n here, xn is available here. So, I have xn available, I have yn available. How do I obtain y of n minus 1? I take this output, delay it. So, multiply by z inverse. Multiply by z inverse, or this represents a delay. So, what is the output here? It is y of n minus 1. This y of n minus 1 I multiply by a. I get a times y of n minus 1 and I add it here. So, two arrows meeting at one place, realize an adder, and then this is my y of n. This, you want minus, so make it minus. You wanted to make me minus here, I would have done that as well, no problem. But I can also multiply by minus a, nobody stops me from doing that, alright. This is the simplest realization of this equation, simplest realization, which is called direct form realization. Now, how can you realize this in the form of a software? You understand software realization of this block? How many of you understand this? Software realization. Can you write a program for this data flow graph? Those who can write the program, can write. Only one can write. Whether we'll be able to or not is a different question. But have a confidence that they can write any given program. C programming, MATLAB programming, whichever. C. How many of you can write C program for this? Raise the hand like this. That shows confidence. This is not a confidence. Neither am I able to see because of the slope of this class. Okay, a few can write. Imagine this equation. How can you write this as a software? Simple. Y is an array, x is an array, and you implement this for n equal to 0 to infinity or 0 to 10,000. Write y of n is equal to x of n minus a times y of n minus 1, where all x, y, a, n are, n is integer, all x, y, a are floating point numbers. So, define a to be floating point number, x and y as arrays of floating point numbers, and then write this equation in a for loop for n equal to 0 to 10,000. Y of n is equal to x of n minus a times y of n minus 1. That is a software realization. You write it in C programming, you write it in assembly language, you write it in MATLAB, you write anywhere. It is all general purpose processor, you are implementing this equation. Alright. What is hardware realization? Put a adder here. assuming that all is floating point, take a floating point adder. These are the devices like RLC are available on the shelf. The adders and multipliers in the form of integrated circuits are available on the shelf. Pick up them. You pick up an adder, 16-bit or 32-bit adder, pick up a 32-bit multiplier, interconnect them like this. Pick up 32 parallel flip-flops. Alright, 7476 is a flip-flop, am I right? JK flip-flop, 4 JK flip-flop. You have to connect 32 such flip-flops in the form of a bus, and you get a corresponding hardware realization of this. Alright, or another way, the same thing can be implemented in the form of a hardware description language. If you implement this in the form of a hardware description language, the hardware can be realized on what is known as a field programmable gate array, FPGA, or a complex programmable logic device. This can be this software, this code of VHDL. It's not called software, it's a hardware description language. Whatever you do in hardware description language can be ported onto an FPGA, which also becomes a hardware realization. Alright, this I think HDL is going to be covered in the course of digital system design in the next semester. Alright, is that clear? Any question on this? So this is system implementation or system realization. Assuming no questions, let's proceed further and start with what is known as discrete Fourier transform. Any questions? Okay. The discrete Fourier transform, last time whatever we have seen, so far how many transforms we have seen with reference to Fourier? We have seen 3 different types of Fourier transforms. One is called Fourier series representation, where the signal that is given is continuous time and is periodic. So far I would write the equations here in time domain and in frequency domain. The first equation in time domain was xt can be written as summation of Cn bar into e to the power j n omega 0 t, n going from minus infinity to plus infinity, where Cn bar was equal to 1 over t integration minus t by 2 to plus t by 2 xt into e to the power minus j n omega 0 t dt. This is known as Fourier series representation. Fourier series. The second expression we wrote was xt is equal to 1 upon 2 pi integration minus infinity to plus infinity x of j omega e to the power j omega t d omega, whereas capital X of j omega is written as integration minus infinity to plus infinity xt times e to the power minus j omega t dt. This is called Fourier transform representation, or continuous Fourier transform, I would say. It's continuous Fourier transform. Next equation we saw was xn is equal to 1 upon 2 pi integration x e to the power j omega e to the power j omega n d omega minus pi to plus pi, where x of e to the power j omega is given as summation of xn e to the power minus j omega n, n going from minus infinity to plus infinity. And this is said to be, this is called as DTFT, discrete time Fourier transform. This is CFT, this is DTFT. I hope you recollect how did we go from here to here. This is the function xt is periodic. Periodic xt. What is Cn bar? Cn bar is discrete. Cn bar is discrete and exists from minus infinity to plus infinity. So values of C in n are infinite. So a periodic continuous time. So continuous time periodic function can be represented in the form of discrete frequencies. When you take t tends to infinity, this function becomes this function. As t tends to infinity, and we wrote Cn bar into t as xj omega. So you got, this is a special case of this. So xt becomes xj omega. Now xj omega is a continuous function. So xj omega is continuous. This is continuous time aperiodic. Xt is continuous time aperiodic. We call it as Fourier transform. It is continuous frequency transform. From here to here, how did we go? We say capital T is small t is equal to n times t. Sampling. We use sampling here. Sampling means xt becomes x of n. So what was this? This remained continuous but became periodic. X of e to the power j omega is continuous and periodic. What about xn? Xn is discrete and aperiodic. This is what we have seen so far. Now the fourth equation that we are going to see is, we are going to use sampling here. Sampling in frequency domain. This was sampling in time domain. Now we are going to use sampling in the frequency domain. What does it mean? It means I am going to define new value x of k, which is equal to x of e to the power j omega evaluated at omega is equal to omega k is equal to 2 pi by capital N. So I am sampling this now. So left hand side becomes x of k, right hand side becomes summation. But this omega, what is omega? Omega is a frequency. What is the maximum value? I mean range of frequency, minus pi to plus pi or 0 to 2 pi. This 0 to 2 pi, I am dividing it into capital N equal intervals. So this omega can be replaced by omega is equal to 2 pi by n times k. This becomes 2 pi by n times k. So x of k is equal to summation x of n into e to the power minus j 2 pi by capital N times n k. Where the impact of this sampling is periodicity. When I am dividing omega by 2, automatically n goes from 0 to n minus 1. So the corresponding counterpart here will become xn is equal to 1 by n summation of k going from 0 to n minus 1 capital X of k times e to the power plus j 2 pi by n times n k. And this is nothing but discrete Fourier transform. This is nothing but discrete Fourier transform. As you see, periodicity in one domain here is associated with discreteness. This is periodic, this is discrete. This is continuous, this is aperiodic. So, sampling in frequency domain, the Cn bar is in the frequency domain, this is sampled version. So friends, periodicity in one domain is associated with sampling in the other domain, discreteness in the other domain. Here the signal xn is discrete and xk is also discrete, both are discrete. Xn is discrete and periodic, xk also is discrete and periodic. Xn is discrete periodic, so also xk discrete and periodic. Alright. So it means in both the domains, the signals are periodic. Alright. So this is also called as discrete Fourier series because of this periodicity. When it becomes aperiodic, in the sense when we are representing the signals that are naturally discrete time and only one period of it exists, in that case it is called as discrete Fourier transform. Value wise there is no change. Alright, only representation wise, some people in some books, when they separate this out, we don't have to consider this to be separate, we are going to consider this to be the same. That is why I write these two equations. But wherever it is separately judged or separately represented, they only write tilde on the cap of it. When a tilde is represented on the top of x, small x or capital X, it represents periodicity. Since it exists from 0 to n minus 1, in all the domains it is represented in 0 to n minus 1. What does this indicate? This indicates that xn is an n point sequence. N point sequence in the time domain is represented by an n point sequence in the frequency domain. An n point sequence, n equal to 0 to n minus 1, k is equal to 0 to n minus 1. In both the domains, the length of the sequence is going to be the same. Alright. So this is in a perspective, all the Fourier transforms representing deterministic signals, satisfying obviously Dirichlet condition. For first two equations you require to satisfy all the Dirichlet condition. For the second two equations you have to satisfy only the absolute summability criteria. If the signals are absolutely summable and if the length of the signal is finite, then that is also not to be considered, that is also not to be required, that is not required to be seen, because a finite length sequence of finite values is always going to give absolute summable. Alright. So the two equations you require to check only the third Dirichlet condition, which is absolute summability. So I rewrite, this is in perspective all the Fourier transform, but as you say, I have said in the first class, wherein you don't require to represent, you don't require to remember all these equations. Only thing you remember that a periodic in one domain is discrete in the other domain. If it is periodic and discrete here, it will be periodic and discrete here, because periodicity in one domain is associated with discreteness in the other domain, and periodicity here will give you discrete here. Alright. So in both the domains the sequences are periodic and discrete. Any questions so far? If it is not clear, I will make it more clear by saying once again, x of e to the power j omega is equal to summation x of n e to the power minus j omega n, n going from 0 to capital N minus 1. Now my xn is only a sequence that is periodic, xn is also periodic, and then I realize this x of k which is defined as x of e to the power j omega at omega is equal to omega k. I am sampling the frequency domain representation, which is equal to 2 pi by n times k. So this equation becomes x of k is equal to summation n going from 0 to n minus 1 x of n e to the power minus j 2 pi by capital N times k times n. Where k is also going to take a value between 0 to n minus 1. And what is this? X of k is called as n point DFT of sequence x of n. X of k is called as n point DFT. What is this n value? It could be anything, 5, 10, 20, 23, 37, it could be any value. So I am dividing the total interval of 2 pi into n equal points.